Quanfluence is a quantum computing company, and when I say quantum computing, we actually build quantum computing hardware. So we are building a quantum computer. So why the excitement? The excitement is because the potential to scale.
Why did you decide that photonics is the way for you as compared to superconducting qubits?
People say you can do it on silicon, but there are issues there as well. We figured that our method of doing photonics was the least hurdle prone.
So let's begin with understanding what Quanfluence is. What are some factors due to which it's easier than other computers?
In photonics, we need lesser amount of cooling. We need to cool lesser amounts of parts. Most of the machine is at room temperature. It looks like a rack, right?
Right.
Yeah. Today and tomorrow, we plan to make it even smaller. Quantum does not allow you to do that. So what will you have to do? You'll have to put some kind of transduction where you go from one machine to the other. And my imagination of that transduction is somehow you go to photonics.
Hi everyone and welcome to another episode of Tech Talks. Today we have Sujoy Chakravarty, the co-founder and CEO of Quanfluence, and we are here at the Quanfluence office to talk more with him and understand what the company does. Hi, how are you doing?
I'm good. How are you?
Good. So let's begin with understanding what Quanfluence is.
Yeah, Quanfluence is a quantum computing company, and when I say quantum computing, we actually build quantum computing hardware. So we are building a quantum computer. Right? So are we building a different kind of quantum computer? Yes. We are building a photonic based quantum computer. So that's basically what Quanfluence is.
So photonic differs from regular quantum computers in terms of the kind of qubits you use.
That's right. So what happens is with quantum computing, there is no established method of doing things. What you normally see are the chandeliers, which is the Google method or the IBM method of doing it, which is superconducting. But that's not the only way. People have done it using various other ways: trapped atoms, ions, silicon spins, etc.
Right. I think I did read somewhere about topological qubits.
Topological.
As well, right?
So one of the methods of doing it is photonics, and well, people haven't demonstrated large photonic computers, but so why the excitement? The excitement is because the potential to scale.
Right.
I think today everyone is talking about scaling computers and how do you scale them, how do you connect them, and in photonics what we say is that the qubits are already photons. They are running around, so it's easier to scale and connect.
Might as well use that.
That's right.
I see. Why did you decide that photonics is the way for you as compared to superconducting qubits?
Yeah, so we did a lot of research on this, right? A lot of work on what is out there, how people are building things, what methodologies exist, how good each of these methodologies is.
Right.
And we found that scaling was the biggest limitation in all of these methods, which is why you don't have a million qubit machine today. Right? And photonics had that promise, the promise that you can go do a million qubits. People say you can do it on silicon, but there are issues there as well. How do you put an impurity in the right position, etc. Right. So every one of them has hurdles. We figured that our method of doing photonics was the least hurdle prone. So even when you talk photonics, there are various ways of doing photonics, and our way is unique. We have several patents filed on our way of doing it, and we clearly know why it is different from the other ways of doing photonics.
Right.
So it's a greenfield technology, research, grounds up. I cannot say that we are better or worse than a competitor, because it's a completely greenfield tech. And our belief is that you have to work on something completely greenfield in order to get that scalable machine. So that's why photonics.
So when you say that it's easier to scale photonics, what are some factors due to which it's easier than other computers?
See, the jury is out there. I mean, everyone will say that your method doesn't scale, my method doesn't scale, right? So what are the factors why we believe scalability is easier? One is, how much cooling do you need? And how big an area do you need to cool, right? So in photonics, we need lesser amount of cooling. We need to cool lesser amounts of parts. Do we need zero cooling? No, I don't think anyone is at a point where you need
comparatively
zero.
room temperature than superconducting.
That's correct. Most of the machine is at room temperature. It looks like a rack, right?
Right.
Yeah. Today and tomorrow, we plan to make it even smaller. And secondly, the reason why photonics is difficult to do or people are struggling is generating enough qubits, keeping the qubits contained, not losing the qubits.
Right.
Right? Because photons are flying around, right?
Right. So if you lose it, then
if you lose it, and you have to keep it contained. But the good thing is that they are flying around. If they are flying around, you can move them.
Right.
So today, when you think of how machines are connected in a data center, it's through photonic links. Right? Now, imagine in quantum there are two machines. You can't just do a copy and put it forward. Quantum does not allow you to do that. So what will you have to do? You have to put some kind of transduction where you go from one machine to the other. And my imagination of that transduction is somehow you go to photonics.
Right.
So then eventually, if you're going to connect machines using photonics, or how are you going to connect machines? Those kind of questions come up. So we are saying, okay, photonics, there are already photons in fibers. You can bring them together, you can connect them together, you can build bigger and bigger systems. So that's what is our idea of why photonics is more likely to scale.
Right. Yeah. I think definitely apart from the technical factors, I think the temperature is one thing that everybody has stressed on, because the cryogenic temperatures that's required for superconducting is quite difficult to achieve as well. Takes up a lot of power too.
That's right.
So,
that's right.
Yeah. Could you talk a bit about like your product, and for us to and for the audience also to understand what you're building here?
Yeah. So the main product, of course, is that photonic quantum computer. Right? So a photonic quantum computer has several parts, right? I gave you a quick tour of this lab and like what is happening in so many places.
Yeah.
This, for example, is an electronics lab. So so that's what we are building. So far the entire measurement system has been built out.
Right.
A lot of the measurement system is electronics. Almost all of it operates at room temperature, and that's what's happening in here. It so turns out that some of these measurement systems are also useful in other applications.
Okay.
Applications like communications, applications like LiDAR, applications like quantum random numbers, QKD, etc.
Right.
So what we do is some of these parts today are commercially available from Quanfluence for people who want to use it in that application. And why do we do it? We do it because that cleans up our parts also.
Right. And I think a lot of academic institutions have been delving into random number generation, QKD as well. So and a lot of them are based in Bangalore.
That's true. We also deal with corporates. There are corporates who are interested in some of these systems, and they also buy some of these devices from us. And if the numbers are small, we actually produce them right here and distribute them as well. So we have a single photon detector which we do in-house. So these parts are available, but they are not our main business. Our main business is that all of these go into that machine which we are building. Right? A part of the machine called the resource state generator has the lowest technological readiness level. That's the part which we are still developing. Some of the work you'll see happening in the lab here. So that's what we basically do. But do we also do something else? And the answer, interestingly, is yes.
Yeah.
So what happened is, as we went along on this journey, we realized suddenly that there is this billion-dollar quantum software industry.
Right.
So what do these guys do? Because I would be one of the first people to say that these quantum computers are not very usable, right?
Yeah, I think the application aspect is still not come up.
So what the quantum software guys do, right, is that they solve a class of problems called optimization. And these optimization problems can be solved on today's machines. Okay, and these optimization problems, we realized, do not need a gate-based quantum computer or even a quantum computer per se. So we have a machine which is an Ising method of doing a calculation. The long and the short is, you can load an energy function onto that, very similar to how you could load on, let's say, a D-wave kind of a machine, and you get the same answer. The machine eventually evolves to the state which gives you the optimized solution. Right? And this is used across the industry. That's what a lot of the software industry for quantum is based on.
Right.
So that is a machine which we have developed in-house. It's there. It does not need cooling. It can sit in a data center rack, and we actually have customers who are using that.
Oh wow!
So that is also a part of what we do. That machine is not a quantum computer, but it fills the gap to a quantum computer as this big quantum computer gets developed.
Right. So you're doing hardware and you're doing sort of hardware for the software also out there.
That's correct. So this hardware is also, we call it quantum inspired because it solves in a quantum like fashion, but it does not really have quantum circuits in it. It has electronics, it has photonics, but it's a quantum inspired machine. It does not solve problems by going one by one as you would in a classical way.
Right.
You load an energy function and it evolves to the right state.
Right. If you could give me like an example of how fast the calculation.
I'll just take a small example to clarify. There is a classic problem called CVRP, capacited vehicle routing problem, right? Where there is a central depot and vehicles with a certain capacity have to service a certain number of certain demand across a city or a country or whatever it is. So it turns out that there are methods of solving this problem.
Right.
And if you solve them one by one, it's an exponential thing and it takes a very, very long time. But there are commercial solvers like Groby, etc., which can solve this problem. Right? So we looked at some state-of-the-art solvers, and for a sufficiently large problem, for a small problem, nobody really cares. When the problem size becomes sufficiently large, some of these things take 15-20 minutes to reach a certain answer.
Right.
A machine like this could do that in about 20 seconds.
Oh, wow.
So that would be 20 minutes to 20 seconds would be a factor of 60 times improvement.
Right. And that's just one problem. When you have a lot of problems that comes on top of each other.
That's correct. So if you're solving a lot of problems, then that speed advantage comes in.
Right.
Also, some things are just not solvable. The problem sizes are too small. You have to solve them in a quantum-like approach, right, or in an energy function loading approach. Do these give you 100% accurate solutions all the time? No. So you can't really use something like this if you're looking for a 100% accuracy solution. But most of the problems which we are talking about here, right, you get to 90%, it's good. If you get to 95%, it's great.
Right.
So that's how these problems operate, and we've consistently shown that these methods of solving problems are faster than traditional methods, and I think that's where this entire industry is, right? The whole software industry around this operates because these methods are faster than traditional methods for a large enough problem size.
Right, definitely. I think in terms of roadmap as well, you have you want to achieve a certain number of qubits by 2026 in terms of quantum computing, and then ahead, if you could share like a bit of your scalability roadmap per se.
Yeah, so the way this operates, this being a greenfield technology, right, is that I don't have a roadmap where I say I have 10 today, 20 next year, 30 next year, etc. Right? Getting my first qubit is a challenge, and we are publicly committed to saying 2029 we will have qubits.
Okay.
So 2029 you have qubits, and then you scale them. We are, a lot of people talk about the million qubit regime, right? That photonics will directly show a million, but our method is, 2029 will show qubits, and then the year after that about 1,000 qubit machine which will be usable, and then you scale it quickly.
So essentially 1,000 qubit system by 2030 is
that's
goal.
What we are thinking. But 2029 qubits, I can't say that I'll get 10 now, 20 now, and so on.
Yeah, definitely. Yeah. Right. I think let's go back a bit into the past of when this company began. You have also co-founded another, I think, semiconductor startup before you come from a semiconductor background, and sort of the startup got acquired by Synopsys, and since then you've delved into quantum. Why did you think that quantum was the bet? That was in 2021 also. That was like quite some years ago.
Yeah. So interestingly, quantum's always been fascinating, right? Because nobody understands quantum, least of all me. So that fascination was always there, but semiconductors is what we knew how to do. So me and my other co-founders in this company, two of my other co-founders in this company, we were the co-founders of that previous company as well.
I see.
So it got acquired in 2018 by Synopsys. That was also a product-based company, high-tech company back in the day. We spent a few years stabilizing that product with Synopsys, and then we were thinking, what next, right? So quantum took our fancy. Lockdown was on, so there was some extra time to study. So it was also fascinating, right? And we believed that this is the next big frontier, and someone has to do it, and someone has to do it from the fundamentals rather than a technology exists and we are also building it in India. Instead of that, we said we will fundamentally do something because we believed that a fundamentally new approach was needed going into this. So we thought of this, we came up with some ideas and we took it to Professor Anil Prabhakar at IIT Madras, and we showed him that this is what we are planning to do. He found it interesting. He joined the team, and then we went to another professor, Sandeep Goel. He found it interesting. He joined the team. He brings a lot of the theory into all of this. And we all sat down together and built this up, and we figured out that this method of doing photonics is what we think is the way to scale this whole thing. And we put in some of our own money to prove it to a certain extent, and went down that path, proved it to a certain extent. This other machine came along in the way. So that other machine came in, we started seeing encouraging results out of it to say, we can at least keep this community engaged until the big machine comes in. Right. So that story is that this machine serves that purpose. We continue to work on that one as well, make it better and better, so that people at least get part of the quantum advantage, and then you move to the full quantum computer.
I see.
So that's how this entire thing came along. Aditi joined us as product/marketing along the way. It's a very important function which we didn't realize in our first startup. Right. But this time we said, okay, let's do that. That's how the founding team was formed. And then we set up on this exciting journey.
Yeah.
Eventually ran out of money, and that's where Pi Ventures and Golden Sparrow and these guys came in, gave us some capital, and we've used that to scale up very quickly.
Right, definitely.
Right? Yeah. So as you will see, as you can see around you.
So I think, considering that you don't come technically, educationally from like a quantum background, does it ever stand as a challenge for you where you feel, if a quantum background was there, or maybe a mentor whose experience in the quantum field would be essential to the startup? So
Anil and Sandeep are completely thoroughly educated quantum physicists.
I see.
Who are professors at very premier institutions in this country. So we have a very, very strong quantum background. Let's start with that, okay? Apart from that, if you talk to our CTO, Biman, I think by now he knows more about quantum than many other people around, even in the field, right? I'm probably slightly weak at quantum, but what people like me, Ravi and all bring in, right, is also converting this quantum into engineering. Because I think a point has come now where the physics needs to be converted into engineering. So that part of the background is also very important. So we understand quantum and engineering, right? People like me, Biman, Ravi. So I think that's the advantage that we have. We have a very strong quantum team, a team which understands quantum well enough and is a very strong engineering team, right? And of course, all of these other people you see are, most of them are educated quantum physicists. A lot of them with PhDs in quantum.
Most of the people in your team, what is the size of your team right now?
We have about 20 people right now.
And where do you do your hiring? Do you go around?
Yeah, we hire from virtually every premier institute in this country. Our hiring is a slightly different thing than normal tech hiring, because one of the other things which I did not mention is we do a lot of chips.
Yeah, definitely.
Why do we do a lot of chips? Because finally everything has to scale. Right? A big tabletop setup has to scale into a chip. Right? And the chip design ecosystem on a photonic chip is not very developed. So a lot of the times people who are building these photonic chips, right, they are building it physics up. I mean, they're thinking about the physics and saying, if I put a structure like this, it will operate in this fashion. And then you simulate it in the physics domain. So even the simulation tools are not the standard tools which a Cadence or a Synopsys would give,
right,
but they would be a physical simulator which comes from an ANSYS or something like that. And so a lot of these chip design people are also PhDs in physics or masters in physics and so on. So the team is broadly classified into the engineering folks who do chips, who do some conversion of the physics into this, and a lot of physicists also, who do some of this fundamental physics, build the models, simulate the models, etc. So that's how the team mix is. Right? Even the guys who work in the lab are physicists.
Do you find it difficult that to get the kind of people that you require for the kind of company that you're building? Do you think it's difficult to find talent out there in India?
It's not easy, but I do not subscribe to that thought that you just can't find this talent in India. There are a lot of extremely talented people that we keep running into.
Right.
We try to hire them. Some of them we can, some of them we can't, for various reasons, including that they want to go for their postdoc somewhere or something like that. But it's not as difficult as I thought it would be, frankly. So I think some of the universities in this country are doing a fantastic job of training the people right.
Yeah, considering you started off with this company at IIT Madras, is that a academic institution you look at to sort of go back to and get talent from?
So IIT Madras, we even have joint development agreements with. We do a lot of work with them, but it's not restricted to them. We do a lot of work with many other institutes as well. Talent, there is absolutely no handshake kind of a thing, right? If you go around, how many people are from IIT Madras? It's not a very large number. So we are open to talent from everywhere. It does not even have to be a premier institution. If you're a good talent from anywhere else, we are very, very open and willing to hire.
Considering that you mentioned also the aspect that a lot of people are, let's say, looking forward to doing further studies, somewhere out of India, and considering the job opportunities in India in such a field, do you think since there are more opportunities outside, a lot of people prefer to go out and not stay back in India in this field?
I think so. I think so. That is true. The job opportunities are limited, and even in these research institutions, how much money is there, how many grants are there. I think those are the things people struggle with. Somebody who works in our company, where else in India can they work? I think it's a handful of places. So then it becomes difficult, right, to build a career in this, especially given that those handful of places are also either startups or academic institutions.
Yeah, I think not a lot
how many big companies hire for this in India? There are no GCCs which hire for this in India, so that leaves you with a very limited size of companies.
Are there other companies, including startups and academic institutions, who all are working in the photonic aspect of quantum or photonic chips?
There are companies today which do that. There are a lot of institutions which do that. So actually one of the things which I found very pleasantly surprising is how much of this work is happening in academic institutions in this country. So it is surprising that they do quite a bit.
Right.
And there are a few other companies as well. I mean, it is encouraging to see that people are starting to think photonic ICs, people are starting to think photonics. There are photonics companies in this country. There are photonics companies in this country who are also getting funding. So that's all good news.
Yeah, that's good to know. I think considering that a lot of academic institutions are working in this, they can only do till an extent of the theory, right? They can't do, let's say, commercialization.
That's right.
So that gets difficult. That's where the startups come in, I guess.
That's correct. That's correct. A lot of the startups also spin out of these academic institutions.
Definitely, yeah. Maybe let's talk a bit about your customers in terms of how you have a range of products. You have the photonic quantum computer aspect that you bring, hoping to bring in soon, but also the photonic chips as well.
Right.
So if you could talk a bit about the kind of customers that come to you, along with maybe, let's say, we can talk about maybe who was your first customer and how you expanded on from there.
Yeah, that's a difficult question because we have 0 customers for the photonic quantum computer, obviously.
Right.
Needs to be proven. But for the components that we sell, we have a large range of customers and across the world. Some of these components have specifications which are superior to competition. Some of the customers are academic institutions. Let's be honest about it. But some of them are, for example, government bodies or people who want to encrypt their data or people who are interested in quantum communications and so on. So we have a range of customers. We ship these parts across the world. Where we have larger name customers are on that other device, the quantum inspired device.
Right.
It's very interesting to see how many companies, how many big corporates are actually interested in that and what's going on there.
Right.
So we engage with some very large names in that space, and we are also running pilots, paid pilots on several of those. The machine is pretty new; it's just 3 or 4 months old, but we are already starting to demonstrate results to them which show that it is a good option to fill in the void while the void exists.
Yeah. Would you be able to name some customers?
Maybe not.
Okay, that's all right.
Yeah.
Let's say I want to talk a bit about these components that you're mentioning. So, were you building your photonic chips as well? We were discussing earlier too. In terms of how much of this raw materials you're procuring from other countries versus also yours is a design aspect, right? So the foundry happens outside. If you could give a bit of a brief around that.
Yeah. So we go to an external third-party foundry. That's also an advantage of the way we do our product. We can actually go to an external third-party foundry. We don't need to build our own foundry. Would we like to do it in our own foundry or a foundry in the country? Yes. But today our foundry support is not bad at all. We can work in an external foundry to build the chips. Components, we try more and more to source locally. But some of the components which we need, like the diodes and some of the fiber arrays and all, we still get from abroad. So it's a mix of that. The IP content is of course 100% ours, but IP content, the PCBs, whatever is available in the country is sourced here. Whatever is not, and it's not a small fraction, is even now, is still imported.
What are some major countries that you source these materials from?
We do source a lot of things from the US, from Europe, and yeah, it's mostly Europe and
Mostly
US.
Europe.
Yeah,
I see.
that's what we source from.
And you have, I think I saw a few machines from Keysight and like a few other
Oh yeah,
companies.
so all the lab equipments come from the standard big players.
Right.
So, but they are also mostly Europe. Some from the US.
Yeah, these are mostly testing equipments, is it?
Testing equipments, yeah. Most of them are test equipments, and some are lasers and stuff, which of course are part of the system. So those are also procured from abroad right now.
Yeah, and you were mentioning to me earlier about the duration it takes for the let's say your design to get fabricated and then come back. Maybe a little into that aspect as well.
Yeah. So today typical foundry times are 6 months. So you make a mistake, you put it into the chip, 6 months later it comes back, you realize there's a mistake, then you wait for the next chip cycle. It's not like you can do it whenever you feel like. So that's probably another 3-4 months away. You have to do the design.
Okay, so you cannot send over your design for fabrication whenever?
Not immediately, unless you're paying a very large amount of money, which we obviously don't. So there are only certain cycles in which you can. So it's the similar thing as the semiconductor industry. A mistake costs you $1 million and 1 year of time. So on the chip, mistakes are very difficult, which is why we have some of these lab setups where we prove things out before we even put it out on the chip. Mistakes are as expensive as in semiconductor.
Yeah, definitely. I think, and some can afford to carry forward the risks, some can't. So I guess.
Yeah, I think mistakes. The semiconductor industry operates on not making those mistakes.
Yeah.
So how you simulate, what rigor you put in, I think we go to that length. We go to the length that a semiconductor person would, because nobody in the industry can afford a mistake if you're building a chip.
Definitely, right. So in terms of like photonic quantum computing, there are quite some other global players out there who are sort of getting into this. There's PsiQuantum, there's other companies. So how do you feel like you differentiate yourself from them in terms of maybe the kind of tech you're building?
Correct. So our tech is different from each of these companies, right? It's very different from what PsiQuantum does, and it's quite different from what Xanadu does, right? And I think that difference is our USP or differentiating factor, right? So I think on the measurement side, things are quite stable, but how we generate a qubit, our method is quite different from some of these other global players. It also changes the amount of money we need to generate it, and so on and so forth. It changes several things, but also means that we have to do a lot of this work ourselves.
Right.
So that's where some of our patents are around as well. So we can't leverage all the work which we see out there. Of course, we leverage some of it. I mean, work coming out of universities and stuff, obviously we love to leverage that.
Right. Yeah. I think in terms of your like the target market per se, India doesn't have that much opportunity right now, do they?
I don't know. I would not want to comment on that because I believe that Indian industry, Indian defense, governments, banks, the banking sector in India is fairly advanced, right? We were the first to do a lot of innovations there. I think all these people have the money and the mind space today to want to invest in this. See, this technology is not a technology which we have left behind, where we are behind. Nobody is forward.
Yeah.
So when the technology is going to take a few years to mature, to develop, etc. I think the Indian market is going to be large, but we do not build for India. What we are building is global, so it will be available globally. But every time that someone says that there is no market in India, we don't know.
Right.
Because
it will come up.
This is technology where India has shown leadership in the past, right? I mean, it is for sectors where we have shown technology leadership in the past, so why not?
Yeah, I think India has been putting quite an effort on quantum as a technology. Definitely in the past 2 years for sure.
Right.
It's come out very actively, and not just like in terms of startups, but also pushing forward academic institutions and partnerships and collaborations. Considering you're based out of Karnataka as well has been pushing the quantum mission very actively. What are some areas that you feel let's say government subsidies or policies have helped you out, and what are some areas that you feel might be, let's say, regulatory bottlenecks or that have been difficulties or technical challenges for you when since you started?
Yeah, the government's always been helpful to us. Right? Interestingly, we have a grant from the Department of Telecom for building some of these components because, like I said, some of these are dual-use technologies. Given we operate in the telecom wavelength, so that money comes in quite regularly as we show progress on those technologies. So they've been useful on that. The National Quantum Mission has been very useful in getting people together, in building the awareness. Building the quantum base in the country. They have also disbursed money now, so the money is available. We are not yet a grantee, but I'm sure things like that will also work out in the future. So I think the government's been very helpful and they have the right mindset. They want to do the correct thing. So that's why we believe that for this technology, we shall not be left behind.
Right, definitely. In terms of bottlenecks, anything? Technologically that
I think the biggest bottleneck for me again is people's mindset, right? Believing that you cannot do something from India, right? Or believing that you cannot design greenfield technology out of India.
Right.
I think, or being dismissive, saying that no, if you are an Indian, just do a copy paste or just do a service. I think that bottleneck or that mindset in Indians and in Indians abroad and in the world in general, I think that for me is the biggest bottleneck.
Yeah, I think the service to product mindset change that I think actively
the service to product mindset and the product to really deep tech product mindset
definitely
change.
I think in terms of when we talk about deep tech and when we're talking about quantum, there's been a lot about how the combination of quantum and AI is going to really change the game. What do you think in terms of that?
Yeah, thanks for inviting me for that talk, and the interest in the people on that was incredible, right? So we believe that quantum and AI are not technologies which compete with each other. They are like perfectly complementary technologies. Right? And what happens is that one will help the other. Take a few examples, right? One of the examples is, as a human being, you're very intelligent, but if I throw a complicated enough math problem, what will you do? You'll take a calculator.
Right.
So similarly, if you throw a complicated enough problem at AI, it has to pick up some tools. So this could be one of the tools, right? The other way is, this could be a tool which is running in the background, continuing to do this math, continuing to solve the world's problems and feeding into AI. So that then the result is that you have an AI trained model on something which quantum is calculating away in the background.
Right. And that increases the speed of inferencing for quantum, the AI as well as.
Exactly. And then the third point where again we see things happening and where we also do something, including with our machine, is when you are doing model training, there are optimization steps in that, or there are steps in that which are quantum friendly.
Right.
So could you use a quantum computer to do training / inference on models, thereby making more efficient models, speeding up model evaluation times, reducing energy and so on. So that's how I see quantum AI, quantum and AI going forward.
So quantum computing in that sense would be a lot more efficient than classical in combination
so
with AI.
it's converting how many your quantum computer is equal to how many petaflops or whatever is a very hard game to play, right? Because quantum is meant to solve problems which you can't classically solve. You throw the entire classical computing of the world together and you cannot factorize two numbers.
Right.
Whereas ideally you can do that using one quantum computer. So the game itself is different. It's not going to replace petaflops. It's not going to replace GPUs. GPUs will continue to do what GPUs are doing. What a quantum computer will do is it will suddenly start telling you, what the interaction between molecules is going to look like, what a particular material is going to come out to be, how to factorize these large prime numbers or such other interesting things. I don't think it's going to end up running an AI model faster.
Right. Okay. I see. I think a little bit more like, let's say in terms of the applications of let's say a photonic quantum computer, when when you do build such a system that's commercially available and people are sort of enterprises are using it, what are these let's say applications that could delve into? I think one I had previously long ago discussed with you was like the traffic management and like trajectory for vehicles as well. So what are these complex issues that it could solve?
Yeah, so when we talk about this, right, the management, the optimization, the traffic management, trajectory for vehicles, etc., you can do that with today's machines, with our machine today, for example, right? Will you need a full-fledged quantum computer to do that? Maybe not, maybe yes, right? But with a full-fledged quantum computer, simulation of the molecules, drug discovery, material discovery, these are things which are extremely hard to do today.
Yeah.
Right? Maybe some speeding up some certain simulations, right? Which today cannot just be done, right? I think to take a new molecule into drug form and give it to a human being and trials and all of that, today is years and years. If you could simulate it, it would not take that long. I think that's where, or climate simulations.
Oh yeah, definitely.
You say you just can't predict the weather because you can't simulate it. The compute does not exist to do that today. With quantum, you could do algorithms which can do that. So I think what else can you do? It's the same thing. When computers came in, people said, oh, it's just a glorified calculator. Once the hardware starts coming in, people are going to come up with these crazy algorithms and do things which are just not possible today. I think that's the promise of quantum, to do what is not possible today. In Star Trek they say, right, to boldly go where no one has gone before.
Yeah.
I think that's what this technology is.
So I think in your roadmap, what would be some interesting announcement or something that we would be looking forward to in the near future, maybe 1 or 2 years?
I think we are very open about what we do. So we will continue to announce all these technological breakthroughs as they come along, these intermediate steps. We will continue to make available the products which come out of building this quantum computer for other commercial use. The quantum inspired machine or the optimizer, you will start seeing use cases of that. You will be able to access it over a commercially available cloud shortly. We are discussing with several cloud providers for that. So all of these announcements will come in 2029. You will hear the announcement of the qubit.
And looking forward to that.
That will be the big announcement.
Right. Well, what about partnerships? Like, what kind of partnerships are you looking forward to? More like with academia, or like, let's say when you talked about the fab part of it, you're currently doing it out of Switzerland, you said, right?
That's right.
So let's say if a startup or like the government was to build like a quantum fab here in India, then would you be willing to collaborate with them?
So at the QIB, I showed a slide saying thanks to our partners, and I could not fit the names on a single slide, right? So everyone is very helpful in this space. So anybody who comes along and we can do something with them, something for them, we are open. Anybody who comes along and can help us, we are very, very happy. And that number is very large. Like if you see who all have partnered with us or who all have helped us in the past, it's a very large number, and it continues to grow. So I mean, everyone, including the government, the media, everyone is very, very helpful at this stage. So we are very happy about it.
Right, right. I think last question that I have, that's more of like just a curious question that I've been thinking. So general like superconducting computer sort of comes in that bigger frame with the temperature controlled inside and the your wires inside and everything. What does like a proper commercial photonic quantum computer look like?
It does not look so appealing. It looks like a rack, like a data center rack. So that's what it will look like. It will be like a data center rack.
And since it's room temperature, you can like keep it.
Yeah, I mean, small parts of it need to be cooled to certain temperature, but that's also an enclosed box.
Right.
So it will always be sitting in the rack. So it will look like a data center rack in the end.
So
not so exciting, but I think probably more scalable.
But still exciting.
Yeah.
So yeah. All right then. I think those were some questions I had. Anything exciting you'd like to mention before we end?
No, I think it's so exciting day to day, right? We don't know how the days go by, and definitely. It's like super exciting, super fun times. Building out this
something
company.
You'd like to mention from India Mobile Congress, where Aditi from your team had gone and.
Oh yeah, so we were invited there as one of the companies, and we got prime time stage time, and the Prime Minister was in the audience listening to us, listening to how things are being built out on the quantum side as well. So it's all exciting times. I mean, everybody cares about this, and we are all set to make this happen.
All right then, on that note, thank you so much for sitting with us.
Thank you.
I had a wonderful conversation, and I had a great time looking at your photonic chip and how you're doing your processes in the lab.
Thank you. Thank you so much.